Good afternoon, everyone. And hello. Hello. Is my voice coming properly? I'm hearing some echo. Hello. Okay, fine. So, good afternoon, everyone, and welcome to the fourth session of this course on applied optics, which is being offered on the NPTEL platform by IIT Roorkee. So, this is the fourth week. So, this is a 12-week course and the fourth week in that course. So, approximately 1/3 of the course is over. And we have 8 more weeks to go. So, as you must have seen up until now, every week there is an assignment that all of you have to attempt, which consists of 10 MCQ questions. And the aim of each of these live sessions is to basically solve some questions from the previous year's assignments so that they help you attempt the current session's assignment problems. So in that series, every Saturday we have a 2-hour lesson where we solve some of these questions. So let us begin with the first question for week 4. Okay, before that, let me, if someone is joining for the first time, let me share the link to the YouTube channel. So that's the link to the YouTube channel where each of these live sessions are live streamed and uploaded on YouTube. So if you happen to miss any of the session, you could go back to that YouTube channel and watch the video. So with that out of the way, let us begin with the first question of week 4. So the first question says, what kind of pattern is observed when two coherent orthogonally polarized plane waves interfere? So let me start the poll for all of you. So yeah, I have launched the poll. All of you please try to attempt this poll. So all of you have about a minute to answer. And then we will discuss. Okay, so let me stop the poll now. And I will share the results of the poll. Hello. Hi, Hi, Suganti. Do you have a question? If not, could you please mute yourself? Okay, that's better. So yeah, so these are the results of the poll. So surprisingly, most of you have got it incorrect. So let me share the correct answer with all of you. So the correct answer is option B, uniform illumination. And why so? This is because orthogonally polarized waves, they do not produce fringes. And this has been discussed in the lectures. We will discuss once again. I'm curious as to why so many people selected circular fringes. I mean, that's a bit weird. But anyway, so interference is what? Interference is basically a result of superposition principle. In the last lecture, I discussed some applications of superposition principle, and I mentioned that interference is also uh, one application of superposition principle. So interference is a result of superposition of waves. So in superposition, what we have is that we have two solutions to the wave equation, and the sum of those two solutions is also a solution. That is the principle of superposition. So let us write down the two electric fields which will superpose. Oh, sorry about this. So first we have the first electric field. Let us call it E1. So this E01 is the amplitude. Then we have this cosine K1 dot R. K1 is the wave vector minus omega t plus epsilon 1. Epsilon 1 is the initial phase. E2 is E02 cosine K2R minus omega t plus epsilon 2 and mod and basically what we have is according to superposition, E, the resultant electric field, is nothing but sum of E1 and E2. And the intensity is time average of mod E squared. So let us find out what mod E squared is. Mod E squared is nothing but E dot E. So this will be, let us open up, E1 plus E2 dot product with itself. So this is going to be mod of E1 squared plus mod of E2 squared plus 2 times E1 dot E2. Now, this term right here, the third term, let me highlight it. This third term is called the interference term, E1 dot E2 term. This is the interference term. And this is where we will see the effect of the polarization come into play. So let us write down what the time averages would turn out to be. So I1 is time average of mod E1 squared t, and I2 will be time average of mod E2 squared t. So let us now find out the time average of mod E squared t, which is the intensity. So this is going to be time average of mod E1 squared t plus time average of mod E2 squared over the time period t plus 2 times time average of E1 dot E2, which is the interference term, time averaged over the time period t. So this will be I1 plus I2 from this definition right here plus 2 E1 dot E2 time averaged over time period t. Now, for orthogonal polarization, So orthogonal polarization, what we have is, we have E1 is perpendicular to E2, okay, which implies E1 dot E2 is equal to 0. And this further implies that the intensity I is nothing but I1 plus I2. And you see that there is no variation with space. There's no variation in space. It is a constant uniform illumination, I1 plus I2. You don't have any space varying term. So this is just a constant uniform illumination. So that's why if you have orthogonal polarizations, then the resultant would be uniform illumination. Now let us consider the general case of non-orthogonal polarization. So in this case, E1 dot E2 will not be equal to 0. Then what will it be? E1 dot E2 will be equal to, from here we can find out plugging in these values. It will be E naught 1 dot E naught 2 cosine K1 dot R minus omega t plus epsilon 1 into cosine K2 dot R plus omega t, minus omega t plus epsilon 2. That's E1 dot E2, and we can further simplify it. Let us simplify further. So E1 dot E2 is E naught 1 dot E naught 2 and then we can use basic trigonometry and open up these cosine brackets. So what we get is cosine K1 dot R plus epsilon 1. So I'm trying to separate time part and the space part so that we can take the time average and see the variation over space. So cos K1 dot R plus epsilon 1 into cos omega t plus sine K1 dot R plus epsilon 1 into sine omega t. This is for the first term. Then we have the second term. This will be cos K2 dot R plus epsilon 2 cos omega t plus sine K2 dot R plus epsilon 2 into sine omega t. Okay, so this is just using basic trigonometry. Now we can further take some things common and multiply. Basically, we will multiply each of these terms and open up further. So we get cos K1 dot R plus epsilon 1 into cos K2 dot R plus epsilon 2 into cos squared omega t plus cos K1 dot R plus epsilon 1 sine of K2 dot R plus epsilon 2 cos omega t sine omega t plus sine of, now with the second term, so the second term over here, this will multiply with both the terms, sine of K1 dot R plus epsilon 1 cos K2 dot R plus epsilon 2 sine omega t cos omega t plus sine k1 dot r plus epsilon 1 sine k2 dot r plus epsilon 2 sine squared omega t. Okay, so we just multiplied each of these four terms to get four terms in the final expression. Now we can, since the space part and time part are separate sinusoid functions, we can take the time average for the time part. Before that, we can use some more trigonometric identities. So what we have is cos omega t sine omega t. This is nothing but sine of 2 omega t divided by 2. And now we can take the time averages. So time average of sine 2 omega t over one time period is 0, which is also the time average of cos 2 omega t over one time period. Now, how do I get that? This is because one time period is nothing but 2 pi over omega. That's the definition of time period. And how do we find out the time average? That's we do 1 over t integral f of t dt, where we integrate over one time period. So here our function is, let's say, sine 2 omega t. So what we will do is we'll do 1 over t integral sine 2 omega t dt 0 to t. And this we can find out. So this is integral of sine is minus cosine. So we get minus cos 2 omega t divided by 2 omega going from 0 to t. And then we have 1 over t over there. So we have this t over here. And this when you put in, so you get minus 1 over 2 omega t cos 2 omega t minus cos 0. And when you put in t equal to 2 pi by omega, so this becomes 2 omega t is 2 omega t is nothing but 2 pi over omega. So this omega cancels, so this makes it 4 pi. Okay, and cos 4 pi is nothing but same as cos 0. So finally what you get is 0, because cos 4 pi is also 1 and cos 0 is also 1. So it cancels and you get 0. Similarly, you can do and check for cos 2 omega t as well. And that also, the time average of cos 2 omega t will come out to be 0. Then we can also find out time average of sine squared omega t. This is so sine squared omega t by trigonometric identities is 1 minus cos 2 omega t over 2. And we just saw that the time average of cos 2 omega t will be 0. So you are left with this 1 by 2. So this is 1 by 2. And this turns out to be same as time average of cos squared omega t over time average. Why? Because again, cos squared omega t, you can write it this as 1 plus cos 2 omega t by 2. And then cosine 2 omega t time averaged, it gives 0. So we are left with just 1 by 2. Now you can see in this big expression that we had, so we have cos squared omega t over here and we have sine squared omega t over here. Only these two terms will contribute to the time average, because sine omega t, cos omega t, this term and this term will average out to 0. So finally what we get is E1 dot E2 time averaged is E01 dot E02 into 1 by 2 because of the time average, and within the brackets we have cos k1 dot r plus epsilon 1 into cos k2 dot r plus epsilon 2 plus sin k1 dot r plus epsilon 1 into sin k2 dot r plus epsilon 2. Okay, this is what we get in the bracket. Now again, using trigonometric identities, we can combine these. So what we will get is, we will get 1 by 2 E01 dot E02 cos k1 dot r plus epsilon 1 minus k2 dot r minus epsilon 2. This is what we get. And this whole argument of the cosine is what we call delta, which is phase difference. So finally, this is 1 by 2 E01 E02 cos theta cos delta, where this theta is the angle between E01 vector and E02 vector. So what we have is, let's say this is E01 and this is E02, it's E01, E02, and this is the angle theta. So E01 dot E02 is nothing but E01, E02 cos theta. So finally, we can write this as square root I1, I2 cos theta cos delta. Why? Because let me come back here. This thing I1, if you find out this time average, it comes out E01 squared by 2, and this is E02 squared over 2 if you perform the time averages. Why? Because what is mod E1 squared? It is nothing but E01 squared cos squared and that big term inside. There is a omega t term over here along with some space part, and when you take the time average, you know that the time average of cos squared is 1. So you take the time average of cos, sorry, it's not 1, it's 1 by 2. So cos squared time average will give you 1 by 2. So that's why from here you get I1 is time average of mod E1 squared, which is E01 squared by 2. Similarly for I2. So finally, the expression for I we can get by putting in all the terms into this expression. So our final result is I equals I1 plus I2 plus 2 root I1 I2 cos theta cos delta. This is one of the most important expressions that you would use all throughout when you study the interference effects. And from here you can see that when theta equals to 0 degrees, you have parallel polarization, and when theta equals to 90 degrees, you have orthogonal polarization. So for parallel polarization, you will get I equals I1 plus I2 plus 2 root I1 I2 cos delta. And for orthogonal polarization, you simply get I equals I1 plus I2. So I hope this clarifies uh, this question, and plus we have also solved for the most general case when dealing with interference effects. And I believe now you understand why it is uniform illumination. Uniform because it is just I1 plus I2 and there is no space varying part. So does anyone have any question in this part? Okay, there is some question in the chat box. Let me read that. Okay, ma'am, could you please write slightly bigger? Okay, I'm really sorry. Is my font size too small? Is it not visible? You want me to zoom in a little bit so that you can take some notes? Yeah, I'm really sorry about that. I'll try to write a little bit bigger from the next questions. For now, what you could do is you could go to the YouTube channel later on, and there you can try and zoom in and see if things are better. Also, I will upload these lecture notes, and you will find the link where I upload these lecture notes on the YouTube channel as well. So when you go to the YouTube, you can click on that link for that PDF version of these lecture notes, and then you can try and zoom in and see if the font size uh, appears to be better after zooming in. Okay, so thanks for pointing that out. I'll try to write a little bit bigger. So I think we can move on to the next question. So let me read out the next question for you. What kind of pattern is observed when a plane wave interferes with a spherical wave? So once again, let me relaunch the poll. Okay, so this time you have a plane wave interfering with a spherical wave, and you need to figure out what kind of interference pattern you would observe. So all of you, please try to answer. Okay, someone is saying hi. Yeah, hi Suganthi. Do you have a question? Yeah, Suganthi, do you have a question? Uh, Please feel free to unmute yourself and ask your question. Or if your mic is not working, you can put in the chat box. Okay, so Jeff is asking for the link to the YouTube channel. Yes, Jeff, I will provide you with the link to the YouTube channel once again. There you go, Jeff. That's the link to the YouTube channel. This is where you will find all kinds of all the videos from the previous live streams as well as any further upcoming live sessions. They will also be live streamed on that YouTube channel. So I hope you go there, and please do subscribe to the channel. It keeps me motivated to upload more and more videos for all of you. Okay, someone is asking a textbook for interference. Okay, so this I had discussed in the first lecture as well. So for optics, I strongly suggest that people look at the book by Professor Ajoy Ghatak. So that's one very good book that you could look at. And yeah, that is a very good book to start with. And it covers a wide variety of topics. So yeah, that's a very good book. I do have that book with me. So if you want, I can show it to you. This another book which is very good. This is Optics by Eugene Heck. Okay, so these are some good books. Just give me a minute. I'll pull it out for you. So these are the books. So this is the first one, which I said, Optics by Professor Ajoy Ghatak. So this is Optics by Professor Ajoy Ghatak. I have the 5th edition with me, but I believe the latest edition is 6th edition. So if you want to purchase that, you may purchase the latest edition. And this is Optics by Eugene Heck. Again, I have the 5th edition for this, but I'm not sure what the current latest edition is. But these are two very good books on optics, and you may start with either of them. Yeah, so when I was an undergrad student, I started off with Optics by Ghatak, and then I moved on to Optics by Eugene Heck. And of course, there are some other advanced texts as well, but these two books should be good enough for you. Okay, so let us come back. Okay, Suganti is asking a question. Ma'am, my friends, 9 members go to a college, so not attend the class. My college is offline class, no online classes. Suganti, what is your concern? I'm sorry, I don't think I understood the concern over here, Suganti. You mean to say your friends are not able to attend these live sessions? Is that what you want to say? College not allow mobile. Okay, Suganti, not an issue. So what you can do, Suganti, is if you are not able to join the live session, what you can do is you can watch the YouTube video. So this is the YouTube channel. So you can go and watch the YouTube video whenever you are not in college. So when you come back from college, when you are at your home, that time you can watch this YouTube video. Okay, so finally, let us come back to our question. Okay, so most of you have answered. Let me end the poll now. So let me discuss the correct answer for this. So most of you got it right this time. So the correct answer is circular fringes. And how do we get that? Let us see. So let us say the screen is at a distance z equal to d from the source. Okay. And again, let us consider two fields. First one from a plane wave. And the second one from the spherical wave. So spherical wave is given as a naught over r cos kr minus omega t. So this one is plane wave. This one is spherical wave. And we need to study the interference of the two. So what is r? R is nothing but square root x squared plus y squared plus z squared. And z is equal to d we have. That's what we are taking. So this will be square root x squared plus y squared plus d squared. And let us take d common. So it becomes d squared, then x squared plus y squared over d squared plus 1. And then square root of that. And then we can apply binomial theorem to get an approximate value. So this is the approximation. This approximation is valid whenever x and y are very small in comparison to d. So in this approximation, we will replace kr with kd plus, so r we will replace by this expression over here. So kr goes to k into this d 1 plus x squared plus y squared over 2d squared. And this, if you open up, becomes kd plus k over 2d x squared plus y squared. And 1 over r we will replace by 1 over d. Now you may ask the question, why in kr I replaced r with this expression, whereas in 1 over r I replaced r simply with this d. So that comes from here. So let us say we have one function f1 which is cos kr, because that is what we have in this spherical wave. So for this we can write down the differential. So the differential df1 is minus k sine kr dr. Whereas if we take the second function as 1 over r, then the differential is minus 1 over r squared dr. Now what you can see from these two is that for large values of r, df2, which is this one, is very small for small variations in r, delta r, for small variation in dr. But what happens to df1? Df1 has this sine kr, it is oscillating. So df1 keeps oscillating. So you keep changing your r, df1 keeps oscillating. So sine kr keeps oscillating between plus 1, minus 1, plus 1, minus 1. It keeps oscillating no matter what value of r you have. Whereas if you keep increasing r, then this term becomes smaller and smaller. So you see very small variations with small changes in r as you go to very large values of r. As a result, 1 by r can be approximated to 1 by d, but cos kr cannot be approximated to cos kd, because cosine functions or sine functions, they keep oscillating. So whenever you have oscillating functions, you need to be very careful what kind of approximations you are using. So let us write the superposition. E is equal to E1 plus E2. And within this binomial approximation, we have a first function. This is the plane wave. And the spherical wave, we are using various approximations. Okay, now we need to find out the intensity, which is nothing but time averaged of mod E squared. So this will be time averaged of mod E1 squared, which is nothing but 1 by 2 E naught squared, plus time averaged of E2 squared, which is nothing but 1 by 2 A naught over D squared. This is coming from the first question over here. This is how we found out I1 and I2. And then we need to write down the cross term, which is the interference term. So the cross term is 2 root I1 I2 cosine delta. So this is over here E naught A naught by D. How I get this? This is because delta is the phase difference. Okay. So what is delta? So this is basically delta, because that is what we get. I is I1 plus I2 plus 2 root I1 I2 into cos delta. Okay, where delta is the phase difference between the two waves. And how you find out? This is because, let us call this delta 2 and let us call this delta 1. So delta is nothing but delta 2 minus delta 1. So if you do this delta 2 minus delta 1, you see that kd minus omega t cancels out from both the sides, and what you are essentially left with is this term and phi with a negative sign. That is how you get this. Now we can use an assumption. We can say let A naught over D equals to E naught. Then what you get is I is equal to 2 E naught squared cos squared. Okay, before doing this, let me just write the whole thing for you. So we get in this assumption, I is E naught squared by 2 plus E naught squared by 2 plus E naught squared cos delta, where this is the value of delta. So when you do this, you get I is E naught squared plus E naught squared cos delta, which is E naught squared 1 plus cos delta, and 1 plus cos delta is 2 cos squared delta by 2. So you get 2 E naught squared cos squared delta by 2. So finally, I is 2 E naught squared cos squared delta by 2. So this gives me k over 4d x squared plus y squared minus phi by 2. This is the final expression. And you see in the final expression, this is the function of x squared plus y squared. So on the screen, what you see is going to be circular fringes because of this term x squared plus y squared. So whenever x squared plus y squared is a constant, that particular the locus of those points where x squared plus y squared is constant will have a constant value of I. And the locus of all points where x squared plus y squared is constant is nothing but a circle. So because of that, because of the existence of this x squared plus y squared term inside the cosine, you get circular fringes. So any questions up until this point? Okay, it seems everything is clear to everyone. So we can proceed to the next question, it seems. Okay, this is a very simple question. I hope all of you get it right. So the question is, when two polarized coherent waves of irradiances I1 and I2 having phase difference delta phi superpose, the resultant irradiance is, you need to find out the resultant irradiance given that you are adding two waves with the following conditions. So let me relaunch the poll. All of you please take roughly 1 minute. Then we will discuss the answer. Okay, so let me stop the poll and discuss the answer. So the correct answer is option B. Oh, let me change my pen. Yeah. So the correct answer is option B. And how we get this is because remember this general equation that we had. This is very important. You should always keep this in mind. So from this general equation, we get this equation over here for the case when theta equals to 0, meaning parallel polarization. Okay. So the first option is the case for orthogonal polarization, wherein you don't see any interference fringes, no fringes. The second one, which is the correct answer, is for the case of parallel polarization. The third one, as you see, is a dimensionally incorrect answer. So as I've always been mentioning, dimensional analysis is very useful in ruling out the incorrect options. So this is incorrect. Why? Because you have the dimension of intensity over here, and here you have I1 times I2, which is dimension of intensity squared. Now, the dimension of intensity can never be equal to the dimension of intensity squared. So by dimensional analysis itself, you can rule out this particular option. And let me just copy this equation over here. This is very important. And paste it over here once again. Oh, I think I'm running out of some space. Let me do one thing. Let me bring this down here. Yeah. Okay. Yeah, so this is the most general uh, expression for intensity. And from this, you can figure out all kinds of special cases. Now we can move to the next question. Two beams produce a sustained interference fringe pattern. They must have A, same frequency, B, different amplitude, C, different polarization, or D, variable phase. So I will activate the poll for all of you. All of you, please answer. Okay, I will stop the poll and share the results now. Okay, almost all of you got it right. So, but I'm still waiting for that one question which everyone gets right. I would be very happy that day when all of you get at least one question absolutely right. We still have 2 more months to go. So hopefully by the end of this course, all of you would be able to get all the questions right, or at least some questions right. So the correct answer, as most of you got it right, is same frequency. Now, in the previous lecture, we discussed the superposition of waves with different frequencies. And if you remember, then we called them beats. So when we added waves of different frequencies, we could hear what is known as a beat frequency. And I can just go back to that lecture and revise that concept of beat frequency for you. Yeah, here it is. So what we did, we added two waves of different frequencies. Okay, so omega, oh, let me activate my pen. So omega 1 is not equal to omega 2. So what we have is different frequencies. Okay, and whenever we added waves of different frequencies, we saw that the resultant was a resultant of cosine terms of two different frequencies. One was the mean frequency, omega 1 plus omega 2 by 2. The other was based on the difference of the two frequencies, which was the low frequency modulation of this high frequency mean frequency wave. And this low frequency modulation was what we called beat frequency. Okay, and beats one could hear whenever this difference is very small. So what we saw is we had this high frequency blue wave modulated by this low frequency green wave to get this resultant red wave. And this was the beat frequency, and we could actually hear this. And to refresh your memory, let me show that simulation to you once again. So this was in the case of audio waves, but this similar concept works for optical waves as well, as we will see. But first, let me show you the demo for audio waves. Let me go to that simulation. Yeah, I hope you can see my Mathematica screen. So here, let me go down. Yeah, here. So we are adding two waves of slightly different frequencies. First one is 440 hertz. Second one is 441 hertz. So the difference is just about 1 hertz. And let me play this for you. You will hear an audio of beat frequencies. So can you hear that? Can someone put in the chat box if they could hear this periodically increasing amplitude and then decreasing amplitude. Increasing amplitude means increasing loudness, and then the loudness decreases, goes to a zero. Then again the loudness increases, then goes to the zero. So that is the phenomenon of beat. And if you listen to the individual frequencies, you would see a sustained sound. See, just 440 hertz, that's a sustained sound, constant amplitude. And 441 hertz, you will not be able to distinguish between 440 and 441. The difference of 1 hertz is too small for humans to actually distinguish. See that? You can't make out whether it is 440 or 441. So 440, now 41. See, 440, 441, you cannot really distinguish. But if I change the frequency to something really high, let's say 460 maybe, then you will see the difference. See, now you can make out between 440 and 460. So 460, 440. But between 440 and 441, human ears cannot really distinguish that much. But when you add the two waves, then you can distinguish the amplitude. It is increasing, decreasing because of this beat. See this. Increase, decrease, increase, decrease, increase, decrease. Okay, so this was about audio beat frequencies. Now I will show you a demo this is not made by me. This is made by someone else. So I'll show that demo to you, which is of visual beat frequencies. So it is a YouTube video. Let me go to YouTube. So can you see my screen? This YouTube screen. Let me make it full screen. Yeah, I think you can see it now. And I will play this video. So in this video, they are adding two visual optical waves, means you can see those waves of slightly different frequencies. And then you see what happens. So they are just showing you the experimental setup that they have to create the superposition of two slightly different optical frequencies. See, now the difference is 0 hertz and they are slowly increasing the difference. As you see, slowly increasing the difference between the frequencies, you see this, and the difference is very small. See, about 1 hertz, about the order of a few hertz, and you see this optical beats effect. See that? And if you increase the difference too much, then the beat frequency is too high, and slowly what you will see, your eyes will not be able to distinguish, and then you will see only a time averaged intensity. Let me replay the video. So when the difference is small, you can see this optical beats. When the difference is 0, then it is just static. And when the difference is too high, then it is the change is too fast for us to for our eyes to actually make out the change. Okay, so that was the video. I'll put a link to this video in my YouTube channel as well. So you can go and watch this video once again whenever you have time. And that way you can visualize what these beats are. So let me come back. So I hope the demo made things a bit more clearer as to what beats are in the context of waves. Now let us proceed to the next question. This is on the famous Young's double slit experiment. I will restart the poll. Okay, in Young's double slit experiment, a laser passes through two identical and parallel slits which are 0.2 mm apart. Interference fringes are seen on a screen kept 1 meter away from the slits. At the screen, the adjacent interference maxima are observed to be separated by 3.29 millimeters. The wavelength of the light is, you need to find out what the wavelength of the light is given the conditions of this Young's double slit interference experiment. All of you, please try to answer the question. I see that nobody has attempted up until now. Please, all of you have about a minute left. Please try to answer before I discuss the solution with you. That way it will be beneficial for all of you, so that you have some idea and you have put in some effort in some direction, and then you can see the correct way of solving things when I discuss it. So I see only one person has answered up until now. Others also, please attempt. I'm waiting for all of you. I will proceed after all of you at least attempt the question. Okay, let me stop the poll now. Okay, so that the correct answer is option C. And how we get it, let us discuss. So in Young's double slit experiment, fringe width is given by delta y is d lambda over a, wherein a is the slit separation and that we are given is 0.2 millimeters. D is the distance from slit to screen, and that we are given is 1 meter. Screen is kept 1 meter away. And delta y we are given is 3.29 mm over here. Why? Because this is fringe width is what? Separation between two adjacent maxima or separation between two adjacent minima. That's the fringe width. So you have two successive maxima points. The distance between those two successive maxima points is fringe width. So if I draw the fringes over here, if these are the fringes, then this distance is what is your fringe width. Okay, and this we are given is nothing but 3.29 mm. So from here we can find lambda is a delta y over capital D. So we can plug in these values and find out. Now it is simple. Lambda is a 0.2 millimeters times delta y, which is 3.29 millimeters, divided by D, which is 1 meter. So this comes out to be 0.658 millimeter squared over meter. So you get 658 nanometers. That's the answer. So the crucial aspect in this question was the concept of fringe width. What is a fringe width? So fringe width is either position between successive maxima or successive minima, or basically any points having the same phase difference. So this and this is also fringe width. Okay. But experimentally, it is always easier to find out positions of either maxima or minima. So that's why we take it as either a separation between successive maxima or separation between successive minima. But yeah, I strongly advise all of you to please attempt the poll before looking at the solution provided by me. Just looking at the solution provided by me is probably not going to be of as much help as when you actually attempt the question on your own and then look at the solution. So the next question, two coherent harmonic light waves with amplitudes 1.6 and 2.8 interfere at some point on a screen. If their electric field vectors are parallel, then Imax over Imin at the screen is, we need to find out what is Imax over Imin and what is Imax and Imin. So where Imax and Imin respectively are maximum and minimum intensities on the screen. So I will start the poll. Please do attempt the poll. So we have completed 5 questions. We are halfway through. 5 more questions to go. And then I have some simulations and demos also planned for you. Okay, I will stop the poll now. So yeah, one of you has got it right. Let me discuss. So we will go back to our expression, this expression right here, which is the expression that will help us. And what we have is we take theta equals 0 degrees. And when delta is 0, then we get I max is nothing but I1 plus I2 plus 2 root I1 I2. And when delta equals pi, then we get I min, which is I1 plus I2 minus 2 root I1 I2. So this cosine delta term dictates when we get maxima or minima. So based on the phase difference, when phase difference is 0 or 2 pi or 4 pi, then we get maxima, and when phase difference is pi or 3 pi or 5 pi and so on, then we get minima. And we are also given these amplitudes. So I1 is E naught 1 squared by 2. We had it in the very first question. We had seen, see, this I1, I2 over here, E naught 1 squared by 2 and E naught 2 squared by 2. So that is what we will use. And E naught 1 we have is 1.6. So this is 1.6 squared by 2. Let me pull out my calculator. 1.6 squared by 2. That gives me 1.28. Similarly, I2 is E naught 2 squared by 2, which is I2 we are having as 2.8. So it is 2.8 squared over 2. Again, I'll pull out my calculator. That gives me 3.92. So we can plug these values in over here. So I max is I1 plus I2 plus 2 root I1 I2, which is 1.28 plus 3.92 plus 2 root I1 I2. Again, putting in the calculator, I get 4.48. Adding up all of these gives me 9.68. And I min is I1 plus I2 minus 2 root I1 I2. So this is 1.28 plus 3.92 minus 4.48. So this is equal to 0.72. Okay. Then taking the ratio, we get I max over I min is 9.68 divided by 0.72, which comes out to be approximately 13.44. So the correct option is option D. I saw that someone had selected option 4 as the correct option. This will be the case when you have I1 equals I2 equals I naught. And why so? You can see whenever you have I1 equals I2 equals I naught, then your final intensity is 4I naught into cos squared delta by 2. Okay. And then I max, actually that will also not give you 4. That will just give you I max as 4, not I max over I min. So I max will be equal to 4 in that case. So I max will be basically 4 times I naught, and I min is going to be 0. So yeah, be careful what is being asked. We can proceed to the next question, which is along the similar lines. This time we have two harmonic light waves with amplitudes 1.6 and 2.8, same as previously, which interfere at some point P on a screen. However, in this case, we have the electric field vectors which are perpendicular. Then I max by I min at the screen is, again, I max and I min are maximum and minimum intensities respectively. So similar question, just that earlier we had parallel polarization. Now we have orthogonal polarizations. Okay. All of you, please try to attempt the poll. Fine. So let me discuss the answer now. So this time we have orthogonal polarization, and as we had in our master equation over here, this time theta is equal to so perpendicular means 90 degrees. That's why what we get is I equals I1 plus I2 simply. Okay. And just to remind, theta was the angle between the field vectors. So perpendicular means that the angle is 90, and that gives us I is simply I1 plus I2 uniform illumination. If you remember the first question, this was the question when we had orthogonally polarized plane waves, then we got uniform illumination. Now in the case of uniform illumination, there is no maxima minima, it is all the same. So this I is I1 plus I2, which is also I max, which is also I min. So as a result, I max over I min is equal to 1. So that's the correct option. So because it is just constant uniform illumination, there is no maxima minima. So if I were to plot it as a function on the position on the screen, this is the screen position versus the intensity, then it is just a flat line. Okay, so moving on. Another question on Young's double slit experiment. So in a Young's double slit experiment, the seventh maxima with wavelength lambda 1 is at a distance y1 from the center of the fringe pattern, and the same maxima with wavelength lambda 2 is at a distance y2. Then y1 over y2 is what? So we need to find out this ratio in terms of different kinds of ratios with wavelengths. So all of you have about 1 minute to attempt the poll. Okay, so I will discuss the answer now. So let me draw first the setup for Young's double slit experiment. So these are my two slits, S1 and S2, which are at a separation A. And then I have a screen, which is a distance D away from the slit plane. So this is my screen. And on the screen, I have some point P. And these are how the rays will go from S1 and S2 to P. And this is the center, O. And this OP is Y, position on the screen. And the angle from the center to the P, this angle is theta. Okay. And then we can find out the path difference between S1 and P and S2P by drawing this perpendicular from S2 onto S1. So path difference, delta, is S2P minus S1P, and for D much greater than A, what we assume is S1P is approximately parallel to S2P. So what we can have is, let me draw. We have this line and this another line parallel, and then one line from the center. Okay, so this is my S2, this is my S1, and the screen is far away, so it all goes to infinity almost, to the point P on the screen. And this is from the center. So this, if this is A, then this is A by 2. And this angle from the horizontal is theta. So, and we are dropping a perpendicular from S2 onto S1. Okay. And sorry about that. And then we are having this line joining S1 and S2. Then this angle right here, let me draw it in a different color maybe. This angle right here, this purple angle is also theta. This is simple geometry. If you do, you can find out. So basically how we find this out. So if I draw horizontal over here, then this angle is also theta. Okay. And because this is horizontal, and that's why if I extend this vertical line over here, as a result, so this is 90 degrees. As a result, this angle is 90 degrees minus theta. Okay. And also this angle is also 90 degrees. Okay. So when you have when you look at this horizontal line S1 to S2 and extend it further, you see angle on a straight line is, sum total of angle on a straight line is 180 degrees. One of the angles is 90 minus theta and one angle is 90 degrees. So the remaining angle, which is the purple angle, has to be equal to theta. So that sum total of angles on that straight line is 180 degrees. So that's how you get that angle also as theta. Thus, this is your delta. This is your path difference. So what you get is delta is nothing but then A sine theta. Okay, it is approximate actually because we are assuming that the screen is very far away from the slip plane. And for small angle theta, sine theta is approximately equal to theta, which is approximately equal to tan theta. Okay, and tan theta is nothing but y over d. Y over d. So for maxima, what we have is path difference should be equal to m lambda. Okay, so and path difference is a y over d. So for the first wavelength, what we have is a y1 over d is m lambda. M is 7 because we want to look at the 7th maxima. So 7 lambda 1. And for lambda 2, we have a y2 over d is 7 lambda 2 because we are looking at the same maxima, meaning 7th maxima. So when we take the ratio of these, we get y1 over y2 is lambda 1 over lambda 2. So the correct option is option B. So 2 more questions to go. Then we will look at some simulations. So this question is about Young's double slit experiment with white light. So if white light is used in Young's double slit experiment, what will happen to the interference bands? Options are no bands will be obtained, or many bands will be obtained as in the case of monochromatic light, but they will be colored except for the central band which will be white. Or option C is very few bands will be obtained, but they will be colored except the center of the central band which will be white. Many bands, last option is many bands will be obtained as in the case of monochromatic light, but all of them will be white. So I will relaunch the poll. Okay, so let me end the poll. So the correct option to this is option C. Very few bands will be obtained and they will be colored except for the center of the central band which will be white. Why? the center is going to be white? Because you have constructive interference or maxima for all the wavelengths at the center. So when all the wavelengths or all the colors combine, they give you white color. Now in white light interference, what happens is each of the wavelength will interfere and give corresponding maxima and minima for that particular wavelength. So um from here, let me come to this. So path difference was AY over D. So this gives me phase difference. What is phase difference? It is nothing but 2 pi over lambda times path difference. So this is 2 pi over lambda AY over D. And in the expression for interference, either this expression or maybe we can look at this expression. I is 4 I naught cos squared delta by 2, where when I1 and I2 are equal. So for that case, we will need delta over 2, which is pi over lambda A y by D. Okay, this is delta by 2. And then you get I is 4 I naught cos squared delta by 2. And you see that because of this presence of this wavelength, each of the wavelengths will have their own interference pattern. And when the wavelength is larger, then the fringe width will be smaller. So fringe width expression also we had. Sorry, the fringe, when the wavelength is longer or larger, then the fringe width will be larger. So you increase the wavelength, the fringe width is larger. So here is this fringe width. So higher the value of the wavelength. So let me draw for, let's say, violet and blue, the interference, violet and red maybe. So let me draw the axis. So what you're going to see is, so you are going to see for violet something like this. Okay, and for red, longer wavelength means fringe width will be more. You are going to see something like this. Okay, so you see that at this point all the colors will have maxima. So this point will be white. Then you are going to see maxima for purple or violet, and finally you would see maxima for red. And then after some distance, again all the wavelengths will start overlapping. Then again you will see white when they start overlapping, and in between you will see basically maxima for all the colors, blue, sorry about this, then green, sorry this is not green, this is blue again. So blue, then green, then yellow, all these maxima will come in between. So yeah, so when your wavelength increases, your fringe width also increases. And when your wavelength increases, then position of maxima also increases. Okay, so this is how you would see white light interference. Finally, the last question for today, and let me relaunch the poll one last time. after this question, then I will show you some computational simulations for interference as well as some demonstration. Okay, so I will discuss the solution now to this last problem for today. So the problem is, in a double slit interference arrangement, one of the slits is covered by a thin mica sheet whose refractive index is n. Separation between the slits is d and distance between slits and screen is capital D. Due to the introduction of the mica sheet, the central fringe gets shifted by delta. The thickness T of the mica sheet is what we need to find. So let me draw the diagram. So we have the double slit arrangement. And we have the screen. And in addition, what we have is a thin mica sheet placed over here in front of one of the slits. So let's say this is S1, this is S2, the separation is small d. This is the screen. Distance between the slit and the screen is capital D. And this is the center. We call it O. And due to the addition of this mica sheet, which has a thickness T, refractive index N, the central fringe will shift to some other point called O prime. And let us say we have a point P on the screen, and these are the rays coming from S1 and S2. Okay, so if we look at the time required to reach the point P from S1, then this is going to be, so the ray travels in free space for some distance and within the mica sheet for some distance. So the ray travels S1P minus T in free space with velocity c, and it travels the distance T, which is the thickness, with the speed v. So this gives us S1P minus T over C plus T over C by N. Why? Because speed of light in a medium is C divided by the refractive index. So this is equal to 1 over C S1P plus N minus 1 T. Okay, so what we see is that for the geometric path length S1P, we have the optical path length For this case, we have the optical path length, which is S1P plus N minus 1 T. Okay, this is the optical path length. And without the fill, if we look at the case, without the fill, the central fringe is at O, and S1O is equal to S2O when there is no fill. But when we have the fill, so with the fill, the central fringe shifts to a position O prime. Okay, so what we have in this case, the optical path S1O prime should be equal to optical path of S2O prime. This means, so optical path length for S1O prime, from here we can find, is going to be simply S1O plus N minus 1 times T, which is equal to S2O prime. Also, from the geometric path difference, we see that S2O prime minus S1O prime is approximately equal to DOO prime over capital D. This comes when we discussed over here. See this from this expression, slit separation times y over distance to the screen. That's the geometric path difference. So that's what we have over here. Slit separation is slit separation times distance on the screen over distance to the screen. So that's the geometric path difference, and combining these two, what we see is that N minus 1 this should be S1O prime, N minus 1 T is equal to DOO prime over capital D, and this OO prime we are given is delta. So from this we get T is equal to D delta over capital D N minus 1. So the correct option in this case is option B. So this brings us to the end of the assignment problems. Now I would like to show some simulations to you. So let me discuss what simulations I have planned for all of you. So the first simulation that I want to show is the general case for interference. So we had this master equation. Let me put that up over here. And if I1 equals I2 equals I0 and theta equals to 0 degrees, then we get I is equal to 4 I0 cos squared delta over 2. So I want to show you as a variation of I1, I2 and theta, the plot of I versus delta. So this is what I want to show you. As you vary I1, I2 and theta, what happens to your interference pattern. So let me go to the simulation, then I will discuss what second simulation I have planned. Okay, so this is my Mathematica screen, and that's the first simulation for today. So let me run this. Okay, so this is what you have. I as of I on the y-axis and delta on the x-axis. This is what I'm trying to plot. So this is my expression for intensity I1 plus I2 plus 2 square root I1 I2 times cos delta times cos theta. This is that expression. And then I'm varying delta from minus 4 pi to plus 4 pi. And then I have on this left side control for I1, I2 and theta. So right now I1 is zero point 0.1, I2 is zero point 0.1 and theta is 0. Meaning I1 equal to I2 equals to I0 and theta equals to 0 degrees. This is what you see. So you see that the minimum point goes down all the way to 0. And this point right here is 0.4. Why? Because this is 0.2, 0.4, 0.6, 0.8 and then 1. So 4 times I1 which is 4 times 0.1 which is 0.4. So this is that case of 4 I0 cos squared delta by 2. You see this. Now if I increase my I1, see I'm increasing my I1 and as the difference between I1 and I2 increases, you see that the minimum point no longer goes down to 0. Meaning your contrast of the fringes decreases. Okay. So these fringes in which the minimum point does not go down to 0, the contrast is poor because you will not be able to distinguish very clearly the maxima from the minima. But if I increase I2 also and make it equal to I1, which is 1, now you see very good contrast between maxima and minima. Again, so this is the case of 4 I0 cos squared delta by 2 because I1 equals I2 equals 1. So this is 4 and then you see minima goes all the way down to 0. Now, if I increase my theta, again you see that the contrast starts decreasing. As my theta is increasing, your contrast decreases and as I go to theta equal to pi by 2, which is the case of orthogonal or perpendicular polarization, I no longer see any interference fringes. All I see is uniform illumination of I1 plus I2. I1 is 1, I2 is 1 and so I see I1 plus I2 and a completely flat line over here. So this was one simulation I just wanted to show you. So the conclusion over here is that when theta equals to pi by 2, meaning orthogonal polarization, you don't see any interference pattern. You see uniform illumination. That's one. You see the best contrast when theta equals to 0, which is parallel polarization. Also, you see the best contrast when I1 equals to I2. When I1 and I2 start differing, then you see that the contrast starts to fall. When theta increases from 0, again you see that the contrast starts to fall. So this is important and you should kind of visualize this thing and see these things for yourself as well. So let's come back. The next simulation that I have planned for you is the classic Young's double slit experiment. I will also show you a demo of the Young's double slit experiment. So the next one is Young's double slit experiment. So in Young's double slit experiment, we had seen that the path difference is AY over D, where Y is the position on the screen. So the phase difference delta is 2 pi by lambda AY over D. So delta by 2 is nothing but YA pi over D over lambda D. And if this causes a confusion, then A is nothing but same as small d as used above over here, which is nothing but slit separation. So I want to show you intensity versus y as we change lambda, d and a. Okay, these are the parameters. So let me go back to Mathematica and show that. So this is the next demo over here. So this is I versus Y. So this is what I plot. I plot this cos squared delta by 2 over here. I'm just right now I'm just ignoring that 4 I naught term. It is just a normalization term, and then I'm plotting it as the position y on the screen for various values of a, b, and lambda. Okay, so now you see, if I increase my slit separation, what happens? If I increase the slit separation, my fringe width starts decreasing. See this? So I increase my slit separation, my fringe width starts decreasing. Okay, this is with slit separation. Now if I increase my distance to the screen, then my fringe width decreases. Okay, now if I increase the wavelength, then again my fringe width increases. So this is the variation. And if I increase the slit separation, then fringe width will decrease. I'll see more fringes. Increase the distance to the screen, fringe width increases, less fringes. Increase the wavelength, fringe width decreases. So again, lesser fringes. So this was about the simulation. Now I want to show you some demonstration of the Young's double slit experiment as well. Although I'm not sure if I will be fully able to show you. So I have also planned a demo. Let's see if it is possible to see that. So let me focus on the camera. So I have this screen over here with me. Okay. And my plan is to show you some interference pattern over here. I'll turn off the light and then we will see the pattern. So I have this laser pointer over here with me. This is a very common laser pointer which is used for presentation purposes. And you can see this laser pointer on the screen over here. If I turn off the lights, you see this laser, bright laser spot over here. Okay. Let me So this is the laser spot that you see. And now what I want to show you is, I want to show you the interference pattern. So I have a hair strand over here. I'm not sure if you can see this properly, but there is a hair strand in the middle. There is a pencil lead over here, and then there are two pencil leads over here. I'm not sure if the camera can focus it properly. And I will try to show you some fringes. So you do see some spreading of the light. Let me turn the lights even more. So it is not so much clear, but you see that this is the laser pointer, just the pointer. And when you put this hair strand, then you see some sort of fringes, not maybe that good of quality, but you do see some effect happening. And I can put it on the pencil lids as well. You do see some spreading, but maybe not that good a fringe. I have something else also. This is two basically two shaving blades kept very close to each other, and then there is a very thin hair strand in the middle of it, pencil lid rather, in the middle of it. So this is trying to create a double slit. So it is two shaving blades and then one pencil lid in the middle. Let's see what happens. So maybe my camera is not able to pick it up very nicely. So you do see some spreading of the light. See some fringes now. See that? Some fringes. Some very closely spaced fringes you can see. See now? 2, 3 fringes. Okay, so this was the demo of Young's double slit experiment. And since I could not show very high quality fringes to you, I have something else for you. So I have a place where I have actually performed this experiment, and I can show you the results of that experiment, because with this webcam, the stuff was not being captured very nicely. So instead of that, I will show you the results taken from a better professional camera. So this is the link to my YouTube channel. So if you go to my YouTube channel and you see this link over here, okay? So if you click on this link, then you will be directed to a website. So you will be directed to this website over here. And here you see this section, academics section. If you click over here, you come down and you see this diffraction project. Okay, if you click on this, then here is a report I had prepared. And in this, you can see some images which are of better quality. It's just the same experiment. So yeah, first you see this white light interference as well. So in the white light, you see that you first see this violet and then you see red. Okay, you can zoom in and see it a little bit better. So this was white light interference, and then you see this double slit. You see these fringes. Maybe I can go even lower. See this. Now this is much better fringe quality because it is taken from a professional camera. So this is for green laser. I have for red laser as well. So between the green laser and the red laser, you see, because red, the wavelength is more, so the fringe width is larger. And you see more number of fringes as opposed to, less number of fringes. In the green, you see fringe width is smaller, so you see more fringes. See this difference between green and red laser. So that is all for today. This was all I wanted to discuss. So this week, the focus was basically interference experiments and mainly the Young's double slit experiment and its variants. So next week, we will proceed and see some other stuff. But that was all for this week. And I hope all of you would be able to attempt week 4 questions and do well in the week 4 assignment. So thank you everyone for joining the session. See you next Saturday, same time, 3 p.m. to 5 p.m. Okay, bye everyone. Yeah, thanks, Soham. Okay, bye. Bye everyone. So the class is over. So all of you could now log out. Yeah, so everyone please log out from the class.
Hello, ma'am.
Uh, uh, the class is over. So if all of you could just log out. Hello.
Okay.